Good evening and welcome everybody. This is Obi-Wan Piz for Simplex Pachinko. We are currently in the middle of installing the Spotify app because, quite frankly, I'm getting fed up with the web app. It's been working less and less and less, and I don't know if they're just trying to get people to get over to the Spotify app. If I were a conspiracy theorist, or if I were a much more cynical person, I would probably be saying with confidence that that is exactly what they're doing. But since I don't technically have the evidence there, it just looks like, it really is hard for me to play the exact group of songs that I want here. How you doing, Zach? And good evening to anybody else who's out there tonight. Okay. Do that. Yes, I want to link my account. Anyway, hope y'all are having a good night. We are going to be doing more cracking the GRE, working on the GRE math subject test, and we're currently up into calculus. Now I am just framing this as using the Cracking the GRE Math Test book from the Princeton Review 2002, mostly in order to get us a framework by which to work all of these problems, by which to teach all of the individual objectives that would be in a standard calculus class. Did I teach the inverse function theorem? So yes. We did. So actually, did I then? Yeah, right. We didn't do any of that stuff. Higher order derivatives. We did the linear approximations. Inverse function theorem. We talked about it. But that is... Oh, you know what? I'm not seeing it in the book. But... I know we definitely talked about it. One of the last couple of meetings that we had. That's really weird. Why do we talk about it if it wasn't... Oh, there it is. Okay. Yeah, the inverse function rule was just after the chain rule. So, like, that's... What are you trying to do here? Oh, boy. I think... I think it's having a problem because I'm logged in onto multiple devices or something. I don't even know. It's weird that this is a problem. Anyway. Yeah, that was what it... Okay. Not even gonna ask. Yeah. So anyway, yes, we did inverse function theorem as a part of like the list of derivative rules that existed. And so the chain rule was like the one that we did right before it. And then inverse function was immediately after, which is also kind of weird from the perspective of like, this is the way I've been teaching stuff for 15 years. That was not in that order, but actually it kind of makes sense. Assuming that people know what implicit differentiation is in the first place, it's basically a non-entity. You can just throw it in there. Okay. So for tonight, we're going to start with implicit differentiation. And hopefully we'll get the backing track in here in just a couple minutes. Copyright free music. Shuffle your playlist. Yeah, sure, whatever. And revolution. Start over. Goodness. Apologies. Maybe a little loud. Okay. Woo! That'll wake you up. I bet somehow this one won't skip. Shocking. Alright, implicit differentiation. So typically when we start looking at functions in general, we already know that they're going to look something like this. Right? Y equals a function of x. Obviously, you can use any variables that you want. You can throw it in with t or s or k or whatever you feel like. But for the most part, y is equal to function of x, as x is your input, y is your output. X is your independent variable, y is your dependent variable. So when we want to differentiate something like this, then typically what we're doing is we're actually saying, okay, I want to take ddx of each of the sides, which on the left is going to yield dy dx, and on the right will yield df of x dx. And again, we end up differentiating each of the actual functions when you know what kind of function it is, what properties you can use in each of those things. However, I also prefer, ever so slightly, that we can actually say, if we want to take the derivative of each side, we can use what's called a generic derivative operator. And some of my colleagues thought I was absolutely insane teaching my students about the generic derivative operator, but quite frankly, it was fine. I teach both ways. I say, look, do whatever feels comfortable, and then they're happy enough to choose one. Now, why do I do this? Well, on the left here we end up taking the derivative of y. That is dy. And on the right, we're choosing to, here we're going to end up needing to take the derivative of f with respect to x. And then we're going to have a multiplier of using the using the chain rule, we then have to take the derivative of the independent variable of that function, which in this case is x, so dx. In theory, we could have left it as dy is equal to df. And in fact, right, as a first step, that's probably actually preferable. So dy is equal to df. But then we say, well, f is a function of x. So if we remind ourselves that f is a function of x, then we'll have to go one further and say we have to do this as a function of x, therefore we need the derivative with respect to x of f, and then times our dx on the outside there. And if we rearrange, we end up getting the exact same thing as what's over there. dy dx is equal to df dx. But I actually prefer this. Now, why on earth would that be? Well, if you've been here long enough, you know that I am a big fan, big proponent, and loved to teach differential equations. So here, right here, and especially right here, are differential equations. They show you what the differentials of each of the variables are, and then we can end up figuring out fairly quickly what sorts of items we might need. Come on. Okay. There we go. Change color. All right, so it allows us to see like precisely what kind of calculus we are doing. In this particular case, we have the derivatives of y and f. F happens to be a function of x, but we deal with that on the next step. And it leaves us the possibility of solving the differential equation directly from the equation that we had left. So most of the time I'm going to do that. I'm going to probably end up leaving it like this top one here. All right, why else does that help? Well, we're going to end up using equations like x squared. Switch back. X squared y to the fifth plus y is equal to 2. Right? And when we get something that says like, hey, derive this following equation, I can take the generic derivative operator of both sides here. On the right-hand side, the generic derivative of 2 is 0, just like any other, right? Because here the function 2, y equals 2, is going to end up having a 0 slope, and therefore its derivative is 0. On the left-hand side, we take the derivative of this sum. So the sum is going to be the primary structure of this whole thing. What does that mean? Well, that means that we're going to take the derivative of each of the addends separately. So x squared y to the fifth plus derivative of y. And then here, this is a product rule. So how do we deal with a product rule? Well, we talked about this last time. We're going to take the derivative of the first term and then multiply it by the second term without change. And then that's going to be added to the first term without change times the derivative of the second term. And then we still have this derivative of y is equal to 0. What do we do then? Okay, we take the derivative of x squared. Well, that's going to be 2x to the first, just like it would for any calculus class. And then also we need to multiply by, you take the derivative of the thing on the inside. In this case, it's just x. So what's the derivative of x? It's dx times y to the fifth plus x squared times, take the derivative of y to the fifth is going to be 5y to the fourth by the power rule, right? Our exponent comes down as a multiplier. We reduce the exponent by 1, and now we have to multiply by the derivative of the inside of that exponent. So now it's just going to be dy. Plus derivative of y is just dy. Right? If we combine like terms, we're going to end up with 5x squared y to the fourth plus 1 times dy. And if we shift all the other stuff to the other side as well, it's going to be a negative 2xy to the fifth dx equals negative 2xy to the fifth dx. Then we end up with a negative 2xy to the fifth dx left over. All right, now what we want is a dy dx term, because here we're looking for when is this we're looking for the derivative of the function y, or well, we're looking for the derivative of the implicit statement up above, x squared y to the fifth plus y equals 2. And here we can do that because now all of our x's and y's can be manipulated around until we get dy dx, which is the derivative of y with respect to x, which is the slope of that particular not function, of that particular equation, that particular curve, there we go, at the point x comma y. So what we can do is shift stuff around until we get dy dx is equal to, and then the other stuff is going to also be in here. Going to divide it off on both sides there, divide off the dx on both sides there, and now we get our answer dy dx as a function of, no, in terms of both x and y, or I guess the slope as a function of both x and y. Yeah, I mean, that's true, because every input, which is each unique point on the in the plane, is going to have a particular value for its slope. So here, negative 2xy to the fifth, all divided by 5x squared y to the fourth plus 1. Okay, so that is our slope function for the particular curve that we had up above. So we had this particular curve. This is important also. Flashbang out. So this was x squared y to the fifth, nope, y to the fifth plus y is equal to 2. So this has this particular curve that we're using as our original curve. You can find the slope at any particular point with one exception. Right, and that is because we said earlier, for continuity's sake, we had to have our derivatives were only going to be continuous where we had continuity for the function, which we have here, right? This is continuous everywhere. Any number x that you want to plug in there's going to be a unique y value that we get everywhere on here. So we could show that. The only issue we have is that it's currently implicit. So in theory, we could go the other way and say that, okay, x as a function of y is going to look like this, and then we could say it's going to be like, plus or minus, which makes sure that it's not one-to-one. But at the same time, we could also prove that it's a function, y as a function of x exists. So if there is a function which could make that work, it's going to be pretty nasty, but it'll be all right. But along with the continuity of just the original function, the original equation that we have, we also need to make sure that the derivative will exist when the definition for continuity is upheld, and also our slope at any particular point is going to be upheld. We also need the slope to be the same from both sides. So we need to do our limit definition This is something that is going to crop up occasionally. All right, the limit f prime at x is equal to limit as h goes to 0 of f of x plus h minus f at x all over h. So first of all, continuity. Continuity of the function must exist means that we have to have the three standard properties. So one, f of x exists. This is over a particular interval, but honestly, like, we're just talking about some random function. Just wherever you're looking at it, just think of it as, look, it's over some sort of domain. Here you go. F of x needs to exist. The limit must exist. So this is the limit as h approaches 0 from the positive side must be equal to the limit as h approaches 0 from the negative side. And actually, you know what? That's not entirely true. We're doing something else here. Boo. No. X goes to C from either side. Of f of x must be the same from either side. So the function values need to be the same from either side. The limit of that particular function at any given point C must exist. C is going to belong to the domain of x throughout whatever domain it is. It doesn't really matter, we're just throwing notation for the moment. So the limit needs to exist, so our function value needs to be the same from the left and from the right. And then also the limit as x approaches C, which is just the generic limit from both directions of f of x must be the same as actually plugging in the value into that function. Okay, I don't need to write that. I could just say f of c, that's fine. Because if it exists, that is the point in the first place. Getting a little rusty, it's okay. Oiling up. That cannot possibly be taken wrong. Okay, f of c has to exist, so we have to be able to plug in the value c, which is in the domain of the function itself. The limit must exist, so we need to be able to plug in numbers from the left and from the right and start approaching the same value. And also, we need to be able to say that that limit is the same as that function value. So that is the continuity of the function. Now, if we want to know the continuity of the derivative, then we need one more. And that is that f prime at c has to be the limit as h approaches 0, f at c plus h minus f at c all over h. Right? Must be true. So you have to be able to find the slope value of that function at every single point along its domain. Or at least every single point that is within whatever domain you're using. Then you're going to say, okay, since the function, the definition of the derivative using limits exists, and it's the same from both sides, then we can not prove. We've shown that our derivative will exist at that particular point. So when we go over to the other one, here we'll notice that as we're coming from the left-hand side, we're approaching a steeper and steeper and steeper value. So our derivative is becoming more and more and more positive, because it's positively sloped as we get closer and closer to 0. Then, suddenly, we're starting at a very steep negative value on the right-hand side. So this value over here is extremely large and negative. So we went from an extreme positive value over here to an extreme negative value over here. That shows us that there has to be a jump somewhere. There will be a jump discontinuity. So we have what's called a cusp at those locations. Cusp at x equals 0 happens to be where y is equal to 2. Right, for this particular one. So 0, 2. Right, so if we plug it in, we'll notice that we get 0 over not 0. So we end up getting a 0 slope. You know, just, it seems wrong. So, so here, right, this does not look like a 0. Oh, 8, there we go. Never mind. Oh my goodness. Yeah, we just didn't zoom in. Okay. Make sure you know what your function looks like. Oh. So this is what happens. That is not a cusp. Actually, you know what? Let's leave that up, just for shame. Famished you in yet? There's a good chance Famish is sleeping. Alright, so there's not a cusp there. Just sort of looked like it until we zoomed in. Yeah, when we plug in 0, 2 as one of our points, then we get 0 over not 0. So our dy dx, our slope, is going to be 0. So that's actually very nice. Let's see. So it does mean that looking at this, we don't have anywhere where there's a sharp change in the slope. So it's looking like our derivative is also going to be continuous for this one. Okay, so that's implicit differentiation. Basically just take the generic derivative of both sides, use all of the rules to break stuff down like you normally would, and when you get down to single variables only, then all we're doing is dx for x's and dy's for y's. Reason being, again, it produces a differential equation, and then you can group all of your dy's and your dx's separately from each other, and then divide through as necessary to get dy dx. Having one on one side and one on the other, obviously, is just much simpler. Okay. Since we're here, the first derivative test is a property by which when you take the first derivative and set it equal to 0, this will show us all possible locations, or shows us the locations of the what are called critical points or critical x values, due to the fact that if it's undefined, it won't be a point, right? There's no point there. So our critical values or critical x values are going to show us the locations where the first now are going to show us important points. So to find them, we set the first derivative equal to 0, or we find where the first derivative is undefined. Now, for the one above, we notice that the denominator has only even powers. And since those powers are only even, and we're only dealing with real numbers in the real plane, then we're never going to get a -1 from that term, and so therefore our denominator will never be 0. All right, never 0, at least this time. So this particular function, this particular two variable function x and y, is not going to have a 0 for a denominator. However, it can have a 0 for the numerator. It is where either x or y are equal to 0 themselves. Or both. Right, Boolean or. So if x is 0 or y is 0, meaning either or both, then we end up with critical values. So where do those exist? They exist literally everywhere on both axes. We already said that we knew that 0, 2 was going to be our critical point because it had a horizontal slope. Okay. So it's never 0. We're not going to have any undefined stuff in the denominator. If our numerator is 0, then we have a slope of 0. The only place where that actually happens is at 0, 2. Everywhere else along the y-axis is empty, and everywhere else along the x-axis, we have the function approaching it, but it never quite reaches it. It is asymptotic. Right, so as x gets bigger and bigger and bigger, we have values that are getting closer and closer to 0, but they are not 0 themselves. Right, if x is infinitely large, then we end up getting an x over x squared. So that's going to be a 1 over, effectively the same as like 1 over x-ish. Ooh, interesting. As y starts getting smaller, this becomes something similar to y over 1. So does that mean that we're going to end up with like a y approaching something other than 0? Nope. Yeah, okay. Just keeps getting smaller, but it is really slow. We're still way down in the 0.01, 0.017, 0.018 value around 30 to 50,000 out. So it's really slow. Okay. So that's our first derivative test. Again, look for zeros of the denominator and of the numerator, and that tells you where our critical points are, critical x values, and then we can determine what kind of behaviors they have as the function approaches that. Right, this is asymptotic to y equals 0, or at least as near as we can tell. There's nothing that makes it look like this is going to get any, like, stop at any other particular value. So as x gets really big, our y's also get really small. Actually, that's something we can do, too. This could be a little practice for limits in general. But if we look at the limit as x goes to infinity and y goes to 0, right, we could figure out what's going on with this. Negative 2x y to the 5th over, oops. Squared y to the 4th plus 1. That is actually potentially a terrible idea, but you know what? Let's do it. We can multiply by 1 over y to the 5th, both top and bottom. And we can divide by x squared, both top and bottom. Take the limit as x goes to infinity, y goes to 0 of negative 2. This is going to be right, an x squared on the bottom. With x here, we get rid of one of them, so it's 2 over x. Y to the 5th divides out, so that's gone. All over 5. We divide by x squared, so that's gone. We divide by y to the 5th, so this is over y, plus 1 over x squared y to the 5th. Okay, so what we've got here is our numerator is going to, so we got a compound denominator that is going to go to infinity. So 2 over infinity is going to go towards 0. Let's turn that around, right? So this is going to 0. This term is going to infinity, because as y goes to 0, 5 over y is going to blow up really large. And then we've got this bit, which is technically indeterminate. However, the other thing that we can do with this is look at it and say, what's going to happen? Like, how are they going to play off of each other? Now, I don't think we can technically do it, because you're going to need to know the relative speeds at which each of these things is going to either infinity or 0. That's so weird. Sorry, I've got 2 different devices that are giving me 2 different times for how long the stream has actually been going. So weird. Right, so 2 different values. We've got a 0 times an infinity. Hello to myself. We've got a 0, we've got an infinity. X is going toward infinity as a square. And y is going toward 0 as a 5th power. But by comparing...
There are some things you'll never understand. Like, why did that person ghost me? When did manspreading become socially acceptable? And how come that dinosaur theme park keeps reopening, given its safety record? But some things you can understand.
Y goes to 0.
Credit score. The more you improve your score, the more you could save on things like credit cards,
Faster than
loans,
X goes to
mobile
infinity.
contracts, and more. It's dead easy to check and completely free. Download the
Is that 100% true?
today.
Might technically not.
Reduced to a tiny whisper. It tries to tell you, I'm running on empty. I don't have much left to give. No need to worry. Your new deodorant is already on its way.
However, this is what it's looking like. So because of that, this should mean that this whole term
Making an ad for Spotify is easy. You just write a script,
should
pick back
also be going to infinity.
and let us create your ad for free in as little as 48 hours. Learn how Spotify
And since
your mix.
this whole term is going to infinity and that whole term is going to infinity, this should end up with the entire fraction going to 0. unless something is particularly contradicting my assessment here. Right, that should be that the numerator goes to 0, the denominator both end up going to infinity, and so therefore the whole thing ends up being a 0 over infinity. It's going to go to 0. Right, the indeterminate form is a little annoying, but you can end up looking at that and saying like, okay, if... No, you know what, it's not even a problem there. The issue is that the relationship between x and y makes this go to 2. Like it's equal to 2. So if I want x squared... We could change it. That is x squared times y to the 5th plus y equals 2. Also, therefore, x squared times y to the 5th is equal to 2 minus y. Right, so the limit as x goes to infinity, y goes to 0 of negative 2 over x over 5 over y plus 1 over x squared times y to the 5th is 2 minus y. And as... oh no. Oh, that's bad. Y is going to 0 from the positive direction. That's not bad. That's okay. Okay. This works. Right, so, again, the top is going toward 0 because x is going to infinity. The bottom has 5 over y. Y is going to infinity. No, y is going to 0 from the positive direction. So therefore, this term is going to infinity. This term has y go to 0, which means that this term goes to 1/2, which is way easier because that's infinity plus a half. So it's infinity. Right? This is going to therefore be equal to 0. So we will get a 0 for that particular limit. That's excellent. Okay. So here's the thing. When you're doing limits like this, sometimes you have to outsmart the problem. If you've got an indeterminate value like x squared y to the 5th, where x is going to infinity and y is going to 0, we've got a problem in that something is going to 0 multiplied by something going to infinity. So 0 should cause this to go to 0. Infinity should cause this to go to infinity. But when they're fighting against each other, they're going at different rates. So we found out here, right, that actual whole term, x squared y to the 5th, is in the original problem here. So shift that over and make it x squared y to the 5th is equal to 2 minus y. And then now, that's so much easier. I only have one thing to deal with. I can just turn that into 1 over 2 minus y inside that little compound fraction. So outsmart the problem. Love it when that happens. Okay. So that is how our first derivative test is going to go. When we look at the second derivative, first of all, what is it? Right? The second derivative is this is the rate of change of the rate of change. Now, what on earth is that supposed to mean? Right? It is the speed at which the slope of a particular curve is changing, or it is going to be the, if you go sailing, right, it's the speed of the boom as it comes swinging around. Right, and looking at how much it's changing over time is going to tell you what its, the other way to go with this is acceleration. How is the speed of something changing? Because again, speed was the rate of change of position. If anybody is new, my name is Obi-Wan Pez, and this is N-Simplex Pachinko, and we're doing mathy stuff tonight. If you have any questions, feel free to interrupt. That's really what this is for. This thing that I'm doing here with Calc 1 is just like a framework to give us some sort of structure while people are not asking questions. So feel free to interrupt, and we'll just zip off to the side somewhere. Alright, so the acceleration is the rate of change of speed. Speed itself is the rate of change of position. So if we look at stuff like position function would have been x of t, speed would have been v of t, or the velocity of t, and the acceleration is a of t. A of t is the first derivative of the velocity, or the second derivative of our position. Meanwhile, v of t is the first derivative of our position function. I don't think I've gotten a warning. Okay. About 5 more minutes until ads. Unless it just jumps me and does it automatically by itself. Again. Hey, there we go, there's a warning. Okay. So our second derivative, again, rate of change of the rate of change, or it is the acceleration, which is the rate of change of the speed. The speed itself is the rate of change of position. And so we can come up with the relationships between all of these things. Right? Position function, x of t, velocity function, x prime of t, acceleration function, v prime of t, or x double prime of t. And therefore, we can also come up with the second derivative test, which tells us that when f double prime of x is equal to 0 or is undefined, this gets us locations. This gets us locations where the function changes its acceleration. Either from positive to negative, or it could in fact be positive, slow down to 0, and then accelerate in the positive direction again. So this can happen with all sorts of different functions. We'll see how it all plays out. But these are called inflection points. Again, typically what you see is that a function will change its acceleration from positive to negative. So essentially, it's kind of like where a trying to think of something you might see on an everyday basis. If you had like a model rocket or something like that, where it would begin accelerating in one particular direction, and then if, as this engine was sort of dying out, you fired another one from the other side, you'd end up seeing this change in acceleration from going this way to now going this way. Or if you used a rocket to go up, right, you'd have the acceleration from the rocket working up, the gravitation from the Earth pulling down, but then slowly, as your rocket started petering out, then all that's left is the acceleration from the Earth. And so now you'd see that all you'd have is there's a point at which our thrust and our gravity are working against each other and even out, where you'd have a 0 acceleration, and then the thrust from the rocket would die out, and all you have left is acceleration due to gravity. Okay, I'm going to go downstairs and cycle that water and do whatever else we need. And we'll be back in 3 minutes to discuss all sorts of stuff in terms of the second derivative test and what second derivatives really mean. And then we'll do some sketching of graphs, i.e. graph sketching. Alright, see you in a bit. Sketchy graphing.
coronation mad about pets. We bake birthday cakes for cats, let dogs share our beds, and even get tattoos of ferrets. Yes, ferrets. Now that's love. You do anything and everything for your pets, and at Pets at Home, so do we. Whether it's expert advice, veterinary care, or grooming, more people trust us with their pets than anyone else. We're all for pets. To verify, visit petsathome.com/all-for-pets.
This is an ad by BetterHelp. We've all had that epic rideshare experience. Halfway through, you're best friends and they know your aspirations to go find yourself in Portugal. It's human. We're all looking for someone to listen, but not everyone is equipped to help. With over a decade of experience, BetterHelp matches you with the right therapist. See why they have a 4.9 rating out of 1.7 million client session reviews. Visit betterhelp.com/Spotify Music for 10% off your first month.
Alrighty, welcome back, everybody. Cool. So, tonight, we are hashtag not sponsored by Northern Monk Dark Matter Imperial Stout. Collaboration. Decadent Imperial Stout. Brewed with Wiper and True. So actually this is two companies that I like. Very dark. Bit chocolatey. Interesting flavors. And not like super bitter or super doesn't taste like coffee, or there's a few other flavors that kind of ever so slightly bother me when they're in Imperial Stout. It's not a real big like punch you in the face kind of thing. It's more of a subtle flavor, and ABV's 8.4, so I might regret that later, but not really. Let's do a quick little workout while we're here. Aww. I'm gonna hate myself for that too, but let's do it. Okay. Hydrants are like the absolute meanest workout that we do in Tang Soo Do Karate. It ends up requiring multiple, like you're doing multiple things, just one after the next, and generally speaking, you don't let up and that's really what makes it tiring, but it's definitely a calorie burner, and it's really good because it has a whole bunch of muscles that you're using all at once. So, try to keep your hands, you can either ball your fists, which is fine, or just lay your lay your hands flat like you would for like push-ups. From here, we're going to take our leg, your choice which one, and just lift it from being bent, from being kneeling on the ground. You're just going to essentially lift it off the ground and then lift it up. Now you know why they're called hydrants. And then down. And then we keep doing this. 4, 5, 6, 7, 8, 9, 10. Hold up. And then we do what's called a front kick. So basically you point your toe and then just snap it out and then bring it back. 2, 3, 4, 5, 6, 7, 8, 9, 10. Hold it out. Go the other way. I don't know what the actual term for that is. One's flex and the other one, I don't remember what the word is. But pull your toes back, or yeah, pull your toes toward your body. So you're pulling your heel, or pushing your heel forward. And then from here, we go up and down. 2, 3, 4, 5, 6, 7, 8, 9, 10, and deal with all the clicking that's going on in your hip. Alright, and then you hold it out here still with your heel pushed out, and you do a figure 8. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. And then we bring it back. You get back into kneeling position. Kind of jut your butt back a little bit. Get the blood flowing. Because that hurts. Alright, it hurts on both sides too, because you're also leaning a bit more out in order to balance the movement. And then we do the other side. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Up and down. 1, 2, 3, 4, 6, 7, 8, 9, 10. Figure 8. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Oh no. I didn't hear it. Shame, shame, huh? Hey, Famish, how you doing? Hello there. That's weird. Oh, wait, hang on. You know what? Yeah, it's because I was on that particular who is it? Let me go back here. Let's add. I think it's browser. Existing blurb. There we go. Yeah, it probably should work now, but anyway. It has to be lower than webcam. Okay. Stream elements has to be lower than webcam. Follower goal. Has to be lower than webcam. Nope. Wait a minute. Timer. Nope. Seems to be fine. Ah. Follower goal. Yeah, has to be above webcam. There we go. Okay. Not a great first day? I'm sorry. Oh, power outweighs. Jeez. That's not nice. Blurp and blurp. Okay. Cool. So, it appears to be there. Let me get over to you in just a second, because well, yeah. They prescribed you glasses? Nice. Live history. There you go.
Shame! Shame! Shame!
Hello there.
Just for you all.
There are some things you should always check.
Yeah, I can always manually go in and force it to happen, just in case it doesn't go off or whatever.
And whether the party is fancy dress. The other thing you should check is your Experian credit report, especially if you're looking to borrow money. It lets you understand
Alright, good times.
what lenders see, so you can increase
So,
your chances of getting the best
hashtag
deals.
not sponsored.
Dead easy to check it, and completely free. See it in seconds. Download the Experian app.
Experian.
I always think of
Speaking of which, I still have to do my trivia.
struggling to know where to look.
You may not understand why it's speaking of, but now the other day we had like a S&P 500 is one of 3 companies or 3 groups that does like credit scores or something like that. What is any one of the other 2? I was like, man, I don't know. Experian. No, it was not. Because it wasn't that kind of credit, I think. Oh well. Yeah, that's a little bit of something else, so we won't do that one. The other thing. I was just thinking about something. It's gone. Man, I'm not supposed to do stuff like that. Talking about differentiation, implicit, stuff with that function. Oh well. Probably remember it later and be like, ah. Okay. So for this, if we want to do the second derivative of the function that we had up above, this gets a little bit trickier just because we are doing implicit differentiation, so there is stuff that's in both variables. Let's take this thing and just copy paste it. That might have been a mistake. Yeah, maybe. There we go. Nope. That's fine. Okay, so if we take this thing and we want to figure out what the second derivative is, then we're going to again take the derivative of, and you could argue exactly what you want to do with this. Again, if we just make this take the derivative of dy dx, well, that may cause problems because we need to take like the derivative of a quotient of two differentials, whereas if we take straight ddx, it becomes much easier because now it's just taking the second derivative with respect to x. Right, this is more straightforward in this particular case. However, we could still go with what we were doing before if we move the dx back over to the other side. We take the derivative of just dy. And then we take the derivative of this whole thing. So negative 2x y to the fifth dx over 5x squared y to the fourth plus 1. So this is going to be pretty ugly, but it's not actually as bad as it could be. So this would be like the second derivative of y is equal to, we'd want to take the derivative of the whole top Federico Enriquez. Yes, taking logs could help, in theory. And yes, logarithmic differentiation is a thing that we usually do in this case. A little short on room, so we're just gonna ... It's fine. Alright, when we take the derivative of a natural log, this is going to end up with the thing. Nope, 1 over the thing. multiplied by the derivative of the thing. Those do not cancel out because they are not squared. It is a first and a second derivative. Those are completely different things. So we're not allowed to do anything particularly with that. Then, on the other side, we want the derivative of... we take the natural log of this quotient, and it's going to end up with the natural log of the numerator, negative 2x y to the 5th dx, which then we could break up again, minus natural log of the denominator, 5x squared y to the 4th plus 1. Ugh. Ugh. Okay, so second derivative of y divided by the first derivative of y equals, we want the derivative of the natural log of, almost had me there, negative 2x. Well, see, that's an interesting problem. Because x could be negative. Or x could be positive. Actually, we do know... I don't think this quite works inside of this domain. We can say it's symmetric in that the slopes on the left are going to be opposite the slopes on the right. We do know that the positive slopes are all on the negative side, so negative x, making this all work would be nice, I guess. But we do end up having a little bit of a problem here. Right, in that both sides of our graph so yes, my issue is that x should be valued from negative infinity to positive infinity. But if we plug in positive values of x into this fraction, we're going to lose them as a part of the domain of the natural log function. Now, in theory, when we take the derivative of this thing, it's not going to matter because it's all going to go away anyway and become a, like, 1 over x type function. So maybe we just don't care. It's probably fine. I know you guys don't care. Something off-heard in my class. Not actually oft-heard that much, but anyway. I do also joke with my students plenty. Alright, so here we end up with, yeah, okay. So that's the other thing, is that this is just going to end up going away. Which I don't know that that's actually true. For the original function. It's probably already incorporated in it somewhere. I'm getting paranoid. So anyway, this is going to be 1 over negative 2x, and then the derivative of that thing is going to be negative 2 dx, so our negative 2's end up dividing out. So dx over x. Plus, derivative of the natural log of y to the 5th. The 5 can come out front and make it 5 times the natural log of y. Take the derivative. And this ends up being 1 over y dy. Plus, here in this case, we get 1 over dx times second derivative of x. Okay. Then minus the the derivative of the natural log is 1 over 5x squared y to the fourth plus 1. The derivative of that is going to be 5 times x squared. We take the derivative, it's 2x times y to the fourth, and then plus, if we leave x squared, we end up getting 4y to the third. And then each of those needs their respective differentials as well. So here we get a dy. Come on. And then take, nope. Take all that stuff, shift it over a bit. Whoops. Good. Totally fits. Would you look at that? Awesome. Like I meant to do it. This is times dx. Right, this is a little less convenient to like move all the stuff around and get all of our dy's, dx's all together in the appropriate locations, but we'll make it work. So we want this to end up with our second derivative of x's and y's to be together. Well, that's going to be inconvenient because it's in the middle of nowhere. Sure, y is implicitly a function of x. But I was trying to start with the generic derivative operator, work out each individual piece, and figure out whether this was going to be at least somewhat convenient to work with. It appears not. So if we go this way, if we go the standard route, which generally speaking all of us were taught, right? This is ddx of negative 2x y to the fifth over 5x squared y to the fourth plus 1. And then if we don't use logarithmic differentiation, we're already here, right? We've already got this stuff. Then we end up getting, so this is going to be the derivative of the top part is going to be negative 2. Derivative of x is just 1 with respect to x times y to the fifth plus, really minus 2 again, x times 5y to the fourth times dy dx. Oh, nope, stop that. all that times the denominator.
Veterinary care or grooming. More people trust us with their pets.
Raise to the negative first.
We're all
Plus the top. Negative 2x y to the fifth. Multiplied by the derivative of that second term. So the derivative of this stuff is going to be a negative 1 times 5x squared y to the fourth plus 1 raised to the negative second. Then multiplied by the derivative of the inside, which is going to be a 10x y to the fourth plus, move that over again.
Spotify will start your morning with the perfect soundtrack to wake up to, or hear again and again every time you hit the snooze button. Tap the banner to learn more.
Leave the first, 5x squared times derivative of the second, 4y to the third, raised to, nope, that's it. That's the derivative of the inside. Cool. Right, dy dx. This is really very inconvenient, unfortunately. Okay, let's take stuff that has dy dx and put it together, and stuff that does not have dy dx and put it together. So, maybe slightly inconvenient, but it's fine. 2y to the fifth over 5x squared y to the fourth plus 1. Okay. That is going to be a negative times negative is a positive. 2x y to the fifth times 10x y to the fourth all over 5x squared y to the fourth plus 1 squared. Minus dy dx. That's a positive, so negative 10x y to the fourth over 5x squared y to the fourth plus 1 plus 2x y to the fifth. Times 5x squared times 4y cubed over this thing squared. Right. So now at least it's on one line. As disgusting as it might be. That's alright. Okay, negative 2 y to the fifth. I don't think I want to bring these together, so we'll just leave them apart. 4th plus 1. Although I technically want to use the second derivative test to find out where there are zeros. Plus 20x squared y to the 9th. I think we're just going to use a calculator. 5x squared y to the 4th plus 1, parentheses squared, plus dy dx, the original, negative 2x y to the 5th over 5x squared y to the 4th plus 1 times the quantity, negative 10x y to the 4th over 5x squared y to the 4th plus 1. Positive 2040 x to the 3rd y to the 8th over 5x squared y to the 4th plus 1 squared. So again, we want to know where, you know what, it might have been prudent. It might have been prudent to leave these in factored form, because a lot of these have that term in it, which can just be divided out. Right? Like we've got all the bits and pieces for it in multiple. Actually, right, we don't have an X here. Okay. Maybe it wouldn't have mattered. But then you could do natural log of y prime prime is equal to y double prime over y prime. Because we're doing this. Okay, so if we do that, let's go. Let's go 1 on that, right? So natural log y prime prime is equal to y double prime over y prime. Fair enough. Therefore, y double prime is equal to y prime natural log y prime. Y double prime would have been equal to y prime. What's that? Yep. Woo! Yes, thank you. I'm doing far too much work. So it's right, if you leave it in terms of some simple ideas, like again, leave it in terms of y prime. Federico, if I had channel points, I'd give you some. I mean, if I had, award points. That's got to be a thing. I'm going to do that for whenever. Probably whenever I actually get my YouTube up to date. That's the problem. I keep streaming. So yeah, don't worry about all this immense amount of stuff, because this is a much simpler expression for it. Yeah. Alright, cool. So when does this equal 0? Okay. So we've got two answers immediately that pop out. We do know that the denominators are never going to be 0 by themselves. We know that we will have y double prime is equal to 0 when negative 2x y to the 5th is equal to 0, but that can't happen because we have a natural log. Or when the when the whole natural log is equal to 0, which means that the fraction 2x y to the 5th, move down, not that far, 2x y to the 5th over 5x squared y to the 4th plus 1 is equal to 1. So when is negative 2x y to the 5th equal to 5x squared y to the 4th plus 1? Alright, so one or both of the x's and y's is going to have to be negative. No, not both. Wow. Okay. Can't be both, because then it would be a negative on the left and a positive on the right. We already know the right side is going to be all positive, right? Because we have even exponents, so there's no way to get negative. X is allowed to be negative. All of our y's are above the x-axis, so so now we say, when does that happen? That's not particularly nice. Right, when are these things equal to each other? Oh, that's interesting. Oddly enough, I don't want to do this, but if we were to move this stuff to the other side, it would set it equal to 1, which means it would be the same as that. We get like this nasty, probably like nested functions and doing weird stuff, so I'm not going to do that, but I just find that amusing. We could set it like in 3 space. We could set each of those parts equal to z, and then say, where do these planes, no, they're not planes, when do these shapes intersect each other? Just out of curiosity. Now I'm kind of curious. Alright, so z equals negative 2x y to the 5th. Ooh, that's fun. Right, so we're going to look like that in 2 space, xy plane. But then when we add the z-coordinate, this is what that's going to look like. That's kind of interesting. I like it. We want the stuff that's all on the negative x side and the positive y side. So that's like all that down here. So our z value is negative. Not that that really matters, but that's a dummy variable. Oh, that's negative. Ah. For some reason I hit 2 instead of minus. That's weird. Alright, and then z is equal to... The other one was 5x squared y to the 4th plus 1. So we have some intersections here. A line, more or less. Ooh. Gross. This is not the Riemann hypothesis. Come on. Okay. It's not a line. Alright, it's this curve here. Which looks to be like some sort of 1 over x variant. Roughly speaking, right? Very roughly speaking. Those are some pretty cool shapes. So yeah, we got some sort of function that goes out like that, and that is the intersection point for all of this.
There are some things you'll never understand. Like, why did that person ghost me? When did manspreading become socially acceptable? And how come that dinosaur theme park...
And then where is everything undefined? Because we could have inflection points anywhere over there as well.
The more you improve your score, the more you could save.
So basically we've got the denominator is not going to cause any problems. Any time that our natural log has internal components there of less than or equal to 0, we're going to have problems. So x equals 0 or y equals 0. But we already knew that. That was not going to be a problem. We got that one place at 0, 2, wherein our inflection point could, in theory, change, but I don't think it does. We definitely have inflection point changes. We definitely have inflection point changes. Do we have a 0, 2 value? Yes. I don't know that it particularly has. It's not going to give me planar values anywhere. Or it's not going to be planar. Okay. If we go back, right? We have inflection points. Again, that's where we change from our graph accelerating upward to accelerating downward. So it's somewhere in here. The problem is I don't know where. We don't have that number from the other side, from the 3D stuff that we had. Boo. Should be 2 distinct points, though. In theory, we could go back to the original and say, hey, x squared y to the 5th is equal to 2 minus y, or then negative... that's not it. Never mind. We don't have those things anymore, sorry. Oh well. In theory, we can multiply an x top and bottom, and manipulate it that way. It's just gonna start getting gross. And again, it's going to reinforce our point 0, 2. Well, 0 and... well, okay, no. We knew that the inflection points were not there. Let's do something crazy. It's probably not going to help any. But. Right, so this should be able to be practically any value in terms of, like, we know that x is negative, y is positive, but we don't have any inkling as far as, like, other ways to manipulate this to make them reciprocals of each other or anything. Right, multiplying them out doesn't help. Right, if we do something really crazy, we can multiply both sides by xy. We end up with a negative 2 x squared y to the 5th times y minus 5x squared y to the 5th times x equals 1. Each of these things become 2 minus y, or we can use the negative to make them y minus 2. So this is 2, y minus 2. times y plus 5 y minus 2 times x is equal to 1. I mean, it gets us x value. Gets us an equation with x as like the primary variable. This is insane. All right, we got like a minute and a half until ads, so why not just play around? This is going to be 2y squared minus 4y plus... I don't think I want to do that, so I think I want to leave these exactly where they are. You know what? Let's even... We can make it a function of x, but then it's going to be a fraction with y's in it. So, I mean... 2y squared minus 4y plus 5... No, stop that. 2y plus 5x equals 1 over y minus 2. Bring the y over. 5x is equal to 1 over y minus 2 minus 2y times y minus 2 over y minus 2. 5x is equal to 1 minus 2y squared plus 4y all over y minus 2. Alright, we're going to ads. See you in 3 minutes. Be right back. Righto. Hey everybody, welcome back. So, what sort of stuff are we looking for here? At this point, this is our solution. So, anytime that this implicit fraction is equal to 1, we're going to have inflection points. Which means that anytime that this is true, we're going to also have inflection points. So now we technically would need like anywhere that xy points from this equation coincide with xy points from the other equation. Then we'd have to be like, okay, well, these xy points are going to be inflection points. Which, like, okay. Does that mean that they're going to have, like, equal x and y values? I think so, right? Anytime the x's from this one match with the x's from the other one, and anytime the y's from this one match the y's from the other one. I feel like that should be true. I'm not sure if that's technically going to work, but let's just check real fast. If we take all this and we say that we want now x equals fraction, y, there's a negative parentheses, y squared minus 4y plus, nope, not that, plus 1, I think it was plus 1, minus 1. I see it. And 2y squared over 5 times y minus 2. Yeah, those aren't getting us the values we want here. We know that the inflection point should be somewhere in here, right? Because we're going from this like curving upward to curving downward. It'd be really convenient if it's this 0 right here. So negative 0.1. So if we plug in negative 0.1, that's not getting us anything there. Yeah. 1.8? No. 1.8 something. That's ugly. Alright. Negative 2y squared minus 4y minus 1. Negative 2y squared minus 4y minus 1. Or 5 times y minus 2. 5 times y minus 2. Okay, x equals. Okay, that's all right. Okay. Right, so we should get an actual function here. That can't be... Well, okay, that's not the second derivative. The second derivative equation is back here. Get rid of that. Well, it has x's and y's, so that's not going to help.
Food snobs get up to 50 pounds off IKEA kitchen and dining until the 28th of September. So can people who don't like coriander. And people who air fry everything. Anyone can get up to 50 pounds off online or at IKEA Leeds. Even competitive bakers. Simply sign up to IKEA Family. IKEA, the wonderful everyday. Available from 8th to 28th of September on kitchen and dining products. Minimum spend £50 for full TNCs. Visit ikea.co.uk/TNC.
You're in your feels when that Pepsi Max mango hits. A fizz of freshness, a switch up to full summer living. You brought flavor to the vibe because you're here for feel good only. Bring out the flavor, bring out the mango. Pepsi Max.
This is 1 over x times that stuff gets us the original equation. No, gets us something in terms of y's only. This over y gets us something in terms of y only. It's gonna be ugly, but in theory we can make this stuff work as well and be only in terms of y. No, because one of them would actually still be in terms of x. We don't have an x equals. I mean, we have an x equals, but it's way down here, and it's really nasty. I mean, this is it. So the problem is that if we tried to like simplify this using the other one, it's probably going to end up becoming something that doesn't quite work. So we may have to think about this for a little bit. Good evening, and welcome everybody from Actual Education, Dr. Gold, and all of your friends over there. My name is Obi-Wan Pez. This is Ensimplex Pachinko. We are doing some stuff from cracking the GRE math subject test, second edition from the Princeton Review 2002. Such a vintage book could not possibly be so helpful, but yes, actually it is, because the math doesn't change that much. Shocking, I know. Yep, no worries, Dr. Gold. Have a good evening, and hope you have a good rest of your night. And welcome on in everybody else. So, on Mondays and Wednesdays, we're doing math-type stuff. So, on Mondays, we're discussing Peter Liljedahl's Building Thinking Classrooms. If anybody knows any math teachers, or you yourself are thinking about becoming a math teacher, this is me pontificating about a particular teaching style that I attempted in my last 2 years of teaching. So I was a community college associate professor, and had been teaching for 15 years up to that point. So I was kind of losing my mind, trying to figure out how to reach the students a bit better, and then I was thinking about, I'm going to have to leave, I'm going to have to, go do something else with my life, and then this teaching style dropped in my lap, and I was like, That is exactly what I need. So, Edoriofor. Good evening and welcome. Wrong accent, sorry. We're looking at implicit differentiation. And what we were trying to do was, our original question was, let's derive this equation here. It's an implicit differentiation, so we work it down and we find out that dy dx is equal to negative 2x y to the 5th all over 5x squared y to the 4th plus 1. We decided that this denominator will never be 0. The numerator is only going to be 0 when either x or y are 0. Turns out that x equals 0 gets us 0, 2, which has a 0 slope. Bingo. Y equals 0 was asymptotic. It's an asymptote. So we're never actually going to reach that. So our first derivative test is telling us that x equals 0 is going to get us some sort of interesting critical x value. And again, y equals 0 being all lit up doesn't really tell us much. We could try to figure out when it... Sophie. Okay, thank you. I will attempt to remember. And then we said, what about the second derivative? Can we figure out where the inflection points are for this particular function? So we discussed all sorts of stuff on what to do with a second derivative test. In order to figure out where the inflection points are, we tried a number of different paths to try to get our second derivative. That was one of them. I don't recommend that. And then we also, Federico suggested that, hey, why don't you just use this? Because this is way easier. So it turns out we had, right, there is the, not quite identity, but we have this property that was coming up. We had the natural log of y prime hidden somewhere up there, and then we were taking the derivative of it. Therefore, that equals y double prime over y prime. When you solve for y double prime, we get y prime natural log y prime. That's super easy. We know what that is. We got that. But the harder part is then trying to figure out what are the x values for which this is true. So now we want, when is y double prime equal to 0? We've got these values, and now what? So we said y double prime is going to be equal to 0 when this part, negative 2xy to the 5th, is equal to 0. Doesn't happen because it's inside of a natural log. Technically, that also makes it undefined, but most likely it's not going to be true for what we're seeing. And if we look at the graph, right, the inflection point is not at x equals 0. The curvature here is pretty continuous. The inflection point we know is somewhere in here. And I think we suspected it was at negative 0.1 and positive 0.1. But now we want to like actually be able to prove it, and so far we haven't been able to. Right? Or our natural log is all equal to 0, which means the interior portion is equal to 1. So that's what we have here. And then we started trying to work out, like, how do we get that equal to 1? We got this thing when x is equal to that fraction. But it doesn't really show us anything except, like, where all of the... like, it shows us a curve. But then, how do we translate that into... what can we get in x comma y that's going to make this work? So again, we think it's around negative 0.1, positive 0.1. How do we prove that? So we're here. We don't really have a whole lot of anything else. We could guess an x value, but again, that's just going to tell us what the curvature is in terms of y. It's going to give us a particular y value, but it's not going to actually tell us anything. Sorry. I got too curious. Forgot this is the page I'm broadcasting. Ah, goodness. So yeah, this is getting slightly annoying. We're trying to make this work. But nothing is quite working out. So it is possible that really we just need to set this equal to 0 in 3D. Negative 2x y to the that was the wrong button, to the 5th over 5x squared y to the 5th. That is not what I want. Y to the 5th plus 1. Natural log plus, no, times natural log of the same. No, you can't do that. So when is this equal to, right, when is z equal to 0? It's that. Yay. So we have something in the xy plane that is now describing what that is going to be. But again, what do we do with it? So x squared, what? Nope. Y to the 5th plus y equals 2. So, like, is it the intersections? Nope, don't do that. No. Won't zoom in where I want it to. Close enough. So you get something really close to 0.2, and we get something really close to 2.4. 0.3 by 1.43. But you know, what's going to be the, well, those are the intersection points. That's not even necessarily going to be the helpful part. Yeah, I'm not seeing how this is going to help us figure out what the inflection points are going to be, which is really too bad, because I really want to figure that one out. But wait, hang on. If that's 5, this should be a 4. Still doesn't help much, but you know, it's something. Because that inflection point should be like here. We gauged it to be around 0.1. Hmm. That's at least nicer. But it still doesn't help us figure out where the zeros are. Whee! Nope, don't do that. Is this actually like above and below? Yeah, I can't even tell. That's not particularly helpful. Okay. So we're having some problems. There is potentially a curve of solutions, but I don't know that we want those to be equal to each other for any reason. We just want them to be equal to 0. And then also we want some other criterion that I'm not able to grasp here. Realistically, we just want the red line to be equal to 0, but it's also nowhere near 0. But clearly, the original function does have inflection points. Because we have a concave up section, we have a concave down section. So now I'm angry. Not really. Now I'm just a little upset, and I want to figure out what this is. But at the same time, like, it's just, I don't think this is going to work for us. Wait. That is completely wrong. Awesome. Right, you can't do that. Because we were looking at... we were looking at moving this over, but that prime stays there. So... That's not how that works. Alright, this is y double prime is equal to y prime times the quantity natural log of y prime all primed. Okay, e is equal to negative 2x y to the 5th over 5x squared y to the 4th plus 1. No wonder things weren't working, we just did it wrong. Multiplied by natural log of that stuff is going to be the natural log of the top portion, negative 2x y to the 5th, minus natural log of 5x squared y to the 4th plus 1, all primed. Now, hear me out. For the inflection points, neither x nor y are going to be 0. And x and y can't yield a 0 in the denominator because they have to be positive and we have a +1. So there's no worry of this entire term being equal to 0, so get rid of it. And make your life so much easier at this point. This is going to be negative 2xy to the 5th. Underneath, the derivative of this stuff is going to be negative 2y to the 5th plus negative 2x times 5 y to the 4th. No, don't do that. Okay. Minus. One over x 5x squared y to the 4th plus 1 under, this is where this 10x y to the 4th plus 20x squared y to the 3rd that needs to be equal to 0. Hi. Negative, negative, negative. Divide 4 of the y's out and divide all the 2's out. So this is y plus 5x, nope, 4 of them are gone, so that one's gone, over 2's gone, and 4 y's are gone, so that's xy. Minus. Equals. Send that to the other side. xy cubed, parentheses, this is probably not the right way to do it, but whatever. Y plus 2x, that's it, over 5x squared y to the 4th plus 1. Don't think there's anything we can really do with this either. Conveniently, anyway. Nope. Derivatives. No, no, no. Nope. Well, that's good times. Okay. That one's a dy dx. And that one's a dy dx. Okay, 1 over x. plus dy dx times 2x is gone, 4 of the y's are gone. So 5 over y times, right? Dy dx times 5 over y. Don't pretend that that's going to be something messed up. All right, then minus 2 over x. No, don't do that. Can't do that either. Damn. 10x y to the fourth divided by 5x squared y to the fourth plus 1 minus 20x squared y cubed over, and then dy dx outside, 5x squared y to the fourth plus 1 equals 0. Over x minus 10x y to the fourth over 5x squared y to the fourth plus 1 is equal to dy dx. Jeez. 5 over y in the negative. Let's reverse. 20x squared y cubed over 5x squared y to the fourth plus 1 minus 5 over y. Okay. Really gross, but compound fractions, we need to multiply everything by 5x squared y to the fourth plus 1 and x and y. It's going to be 5x squared y to the fourth y minus 10x squared y to the fifth, which is also something from the very beginning. No more fractions. Equals dy dx times 20x cubed y to the fourth minus 5x times 5x squared y to the fourth plus 1. That can be shifted under. No. That's dy dx. We already know what that is. Okay, these can be combined, because that's going to be a negative 5x squared y to the fifth. X to the third y to the fourth. Ugh. 5x cubed, 25x cubed. Y to the fourth plus 1 parentheses. Right, we're trying to solve for some x and y which are not 0. fifth
reduced to a tiny whisper
plus
and tries to tell you.
dy dx is, yet again, that thing.
No need to worry.
Negative
New deodorant is
2xy
already
to the
on its way.
fifth.
Arriving today with Amazon Prime. Everyday essentials delivered fast. It's on Prime.
Divided by
Cut-off times and T's and C's apply. See product page when ordering.
Sometimes you just
5x squared y to the fourth
Something creamy, full of flavor, something a bit
plus 1
yeah, try
times.
Yuzu in
Here,
Two delicious milkshakes.
that negative distributes in, and we get a negative 5
Creative flavors
x to
inspired
the
by
third
your
y to the
favorites.
fourth
The perfect
minus
gift
1.
meal, a reward for a busy day or just a little treat for being you.
Give your treat more taste with new
That is
Yuzu
so
inspirations.
ridiculously close to the denominator. I hate it.
Making an ad for Spotify is easy. You just write a script,
Absolutely hate it.
pick background music, then just create your ad for free in as little as 2 minutes. Learn how Spotify and
But just close enough that I can't act. Ooh. Wait. 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 That's not a 1. It's a minus. I know. Minus is still outside. 5x on the inside. Alright, so it's a minus 25 in makes minus 5. And then plus that. Nope, no, that's going to become a minus 2. 5x. That doesn't work either. So close on like so many different fronts. It's a little ridiculous. I hate it. Okay, that negative can be factored out to divide or multiply by that negative out front, so that's gone. Okay. Negative 5x squared y to the fifth equals 2xy to the fifth times. This can be also gonna hate it. 5x squared y to the fourth plus 1 times x separated plus 4x. If we split the 5x into two parts, factor out the x part of it, we get a plus 1, which allows this one single term to divide out with 5x squared y to the fourth plus 1 in the denominator. However, other terms can't do that. You've joined the flailing wildly part of the stream, so good luck. Fifth is equal to 2xy to the fifth times 1 times x. And that is it. This one's done. Then we have plus 2xy to the fifth times 4x all over still 5x squared y to the fourth plus 1. This can be subtracted over, and we get negative 7 x, yeah, x squared y to the fifth, right? Because this x and that x join up. And we subtract it off from both sides. Okay, okay, is equal to 2x y to the 5th. Nope. 8x squared y to the 5th. Divided by 5x squared y to the 4th plus 1. Boy. X squared y to the 5th could be divided off of both sides. So negative 7 is equal to 8 over 5x squared y to the 4th plus 1. Multiply that over to the other side. We end up with a negative 7 times the quantity, 5x squared y to the 4th plus 1 equals 8. Oh my goodness. We're getting close, but like this isn't quite going to work the way I want it to. Negative 35x squared y to the 4th minus 7 equals 8. Negative 35x squared y to the 4th equals 15. Negative 7x squared y to the 4th equals 3. Yup. Can't do it. Stuff on the left has to be positive. The stuff on the right has to be... The stuff on the left has to be positive, but now we get a negative stuck out in front of it. So that would mean that the right side would have to be negative, but it can't be, because now it's a positive number. So there is... I did something wrong somewhere in this, which is not going to work nicely. To try to figure out what I did and when and how. That is a most unfortunate. Okay. When we're looking at actually trying to figure out what things are going to get us, or higher order derivatives, or implicit differentiation, all that good stuff. Okay, when we actually figure out something useful. Oof. What is the second derivative? Of f of x equals log of x. Now, keeping in mind what they really mean is the natural log. So we're not doing this in terms of log base 10. This is actually log base e. And actually... Okay, so f prime of x is going to be, we take the derivative of the natural log, it is 1 over the natural log of x, and we take the derivative of that by the chain rule, and we get 1 over x. Multiplying by both, by x, both top and bottom, is going to get us that we have x divided by natural log of x. F double prime of x is going to take that and take its derivative. So we're going to take the derivative of the top, and we just get 1 divided by natural log of x. Okay, plus x times the derivative of the realistically, I write this as x times natural log of x raised to the negative first power. So this is going to be negative 1 times natural log of x raised to the negative second times the derivative of the natural log of x, which is 1 over x. So our x and 1 over x end up dividing out until we get 1 over natural log of x is double prime x minus 1 over parentheses natural log x squared. Oh, shoot. That derivative goes... I forgot or something. That derivative of natural log of x goes to the top. So that is actually times 1 over x as a whole. Now this just makes... yeah, this is all wrong now. Boo. This is equal to 1 over x natural log x. Good enough. So when we do the second derivative, we're going to take, this is 1 over, right? This is just this stuff raised to the negative first power. So this is going to be negative 1 times x natural log x raised to the negative second power plus, no, multiply by. Chain rule, what's the derivative of the inside of this? So we take the derivative of x, we get 1 times the natural log of x, plus x times the derivative of natural log of x is 1 over x. So this now becomes negative parentheses natural log x plus 1 all over x natural log x parentheses squared. Yep. X natural log x squared negative parentheses 1 plus natural log x. Yep. If anybody has another question to ask, we do have a few minutes here, but apart from that, we will go for this last question here. Right. So when we're looking at curve sketching, we're looking at what are the values of the derivatives and the second derivatives actually going to mean within the context of the graphs of the functions. So here, when we take f prime of x, we have a few possibilities, right? If f prime of x is greater than 0, f prime of x is equal to 0, or f prime at x is less than 0. The first derivative represented the motion or the velocity of a particular object. So in this case, we see, okay, if f prime of x is greater than 0, this means our slope is going to have a positive value, so it's going to be going upward. So that means that the function is increasing. If f prime is less than 0, we have a negative slope. And so the function is decreasing. If the slope is 0, then we have a 0 slope. And we could probably call that quote-unquote flat. Right, so we have an area where it's not going to be increasing, nor is it going to be decreasing. It is flat. So this can be just a single location, like we saw with our prior function. Right, this comes up like that and then back down like that. So at the top, we're reaching a 0 slope. F double prime at x. F double prime at x is going to be either greater than, less than, or equal to 0. Also, oops. Right, if it is greater than 0, F double prime, this means it's accelerating upward faster and faster and faster. So our slope is increasing. So this looks something like this. But it could also be the other side of that too. We have a slope decreasing. Oh wait, that's not right on this one. Either it's a slope like this, or it is a slope like this. We don't know which. If we have f double prime is less than 0, then our slope is decreasing. So we're going to have a slope that works like this.
He's having a blinder. He's clipped the post. He's
Wait.
looking formidable.
Increasing. Arg. Right, or like that. Slope is increasing. It means that we have a negative slope, but it's getting smaller. Yeah, that one.
Honey Power Games gives you more chances to win. Imagine that. Life with more chances.
Slope value is increasing, so it could be negative and increasing towards 0. There we go. And if the slope is decreasing, that means we're becoming more negative.
One spin per player per day. Each prize carries individual T's and C's. Eligibility rules and T's and C's apply. 18+ begambleaware.org.
Right, so we go from a high positive slope to a low positive slope. That's becoming more negative. Right. Oi. Alright, or if our slope is equal, or no, if our curvature, if our rate of change of slope is equal to 0, this means that we have a constant slope. Something like that. Either it's going up, it's coming down, or it's just flat. But the slope is not changing. Alright, so for each of these, this actually gives us a unique determination for whether our slope is increasing or decreasing or flat, and our curvature, our second derivative, our acceleration, is positive or negative or flat. Or positive, negative, or doesn't change, really, for either of these. Alright, so we got something that looks, roughly speaking, like this. Okay, I think we're going to call it there. We have only a little bit of time left till ads start, so we're going to get out of here. Let you all have a good evening. We will be back possibly tomorrow to play some games. Most likely Elite Dangerous, because we have a big event going on that's all about mapping planets and trying to get some good signal stuff going. Anyway, I don't know. It's going to be interesting. So, we will possibly be back, like I said, tomorrow. We'll be off this weekend for the Friday stream. And then we may be back for... We'll probably be back for Sunday. Interesting. We got somebody who just came on. Probably for... I'm going to see if they have... They're a sort of new person who is on the math category. They have 4 followers. We're going to absolutely scare the crap out of them. And they say math and art and stuff. So I think we're going to start a raid over there. Oeo Elemeno. Oeolmno. I don't know. We'll see how it goes. Anyway, hope you all have a good, what's tonight? Wednesday? And we'll see you possibly tomorrow for Thursday, playing something as kind of an extra, because again, I'm not here Friday, and then we'll be back on Sunday. Probably also depends on whether or not I actually do anything. I may feel like just skipping tomorrow, so we'll see how it goes. Anyway, hope you all have a good rest of your evening, and we'll see you later. I will certainly be back on Monday for more Peter Liljedahl Building Thinking Classrooms. In the meantime, I hope you all have a lovely rest of your weekend, whenever I see you next. And, yeah, good times. Stay mathy. My name is Obi-Wan Pez. This is N Simplex Pachinko. Catch you next time.